Good morning. I'm Rafael from UC Berkeley in California. I graduated in December with a bachelor's in electrical engineering, and I've been working on what we're calling the green for the rest of the year until about July. So I'm going to talk to you a little bit about who we are, what the lab I work in does. Then I will tell you a little bit about what the devices that we're designing, the high-level requirements for what we wanted to achieve, how we did it, and then what we found as results when we finished constructing and testing it, and then what we could possibly do with it in the future. So who are we? So I work in the lab of Professor Paul Wright, and the group that I work in is actually a collaboration between the Berkeley Manufacturing Institute, the Center for Information Technology in the Interest of Society, and the Berkeley Center and Actuator Center. So the work we focus on in our lab is particularly MEMS and energy scavenging. So we do things like current, pressure, energy scavenging from vibration, thermal, and magnetic stuff, as well as a few other side projects that all focus on wireless, low-power sensing type of work. So what exactly is the green device? So here's a picture of the green next to a US penny, and what it is effectively a small, low-cost sensing platform that you can use in a mesh networking configuration and be used for sensing various types of quantities around the lab, a factory, industry, or any type of location where you want to gather sort of smart grid type of data. Well, the way we came up with it was the MEMS and energy sensing group that I work in does things that involve non-intrusive energy sensing. So we look at things like circuit breakers, underground cables, and this particular work that inspired this was a gas pipeline project. So where we built a few prototype nodes that were somewhat larger, that have a commercial radio on it, with a microcontroller from TI. They have a commercial accelerometer and a somewhat large coin cell. So we're actually looking at a 1 amp hour coin cell right here. This work was a success, but then we thought, well, can we take the same design for similar energy sensing applications and make it smaller? How small can we make it? So the three basic requirements that we had for a device like this was, one, that we have to have a processor and a radio. We have to have a power supply, energy storage type of component, and we have to have a sensor because we're interested in measuring quantities about the environment or power and energy. So there are several types of wireless networks we could be using. Things that exist are Zigbee-compatible radios, we have Bluetooth radios, and some proprietary networks. For the energy storage, we have two requirements. One, that the device can operate for an extended period of time on its own, and it has to be rechargeable because we don't want to service it. And it also has to be able to source high current pulses for radio transmissions. And the sensing components have to be small, low-power sensors that are sensitive to the quantities that we're interested in. So down here is the block diagram of what the system might look like. We have the radio module with the processor, the power supply, and in this case, magnetic sensor. So the sensor the controller that we chose for this is a part from Atmel. It's an 80 mega 256.4 RFR2. It's a Zigbee-compatible 2.4 gigahertz radio. And the reason we chose this was twofold. Mainly because, one, when I built this, I was familiar with the Atmel architecture, and two, a lot of people in our lab were not exactly software engineers or had a programming background, so we wanted to make it Arduino compatible. I'm sure many of you might be familiar with the Arduino platform. It's a simple sort of easy to program type of environment, so you can actually do very simple, very complex programming in a very simple IDE. So you can make this chip compatible with that. And what you see down here is the minimum circuitry required to implement this radio. So we have the basic components of some power filtering, some clock sources, and an antenna front end for the radio transmissions. That's all you really need to feed data in from sensors and transmit it via the radio. So here's actually what it looks like. So the chip itself comes in a 7.5 by 7.5 millimeter package. So the conceivably smallest size we can make this with that chip is something on that order. So with some margin for mounting the chip and the size of the board, we come up with a minimum possible size of 7.5 by 7.5 millimeters. And the way that worked out is we took the entire top side of the board to mount the chip, and the entire bottom side to provide the passive components and sensor attachment pads around the edge. So you can see here what a constructed radio microcontroller board actually looks like. So this integrates everything you would need to sense sensor inputs and transmission. So we believe we did a decent job at sizing it with this. So the next thing that we need to be designing is a power supply that can match the size. As I mentioned earlier, we have a few requirements. One of them is we have to have a footprint the size of the radio. So it cannot be any bigger than what was previously shown. We have to have it to be rechargeable, and it has to be able to source both currents for short periods of radio transmission. So the first three are actually relatively easy to satisfy because you can get very small lithium batteries that have relatively high capacities for their sizes. And the part we chose for this work was a ML621 type lithium manganese rechargeable battery. But there's a small problem that these batteries are optimized for high capacity and low discharges, so they have a very high internal resistance, which means that you cannot draw high currents out of them for radio transmission. It's just the voltage will drop immensely when you try that. So we need a solution around that. So the solution we came up with for this is we combined a supercapacitor with this battery, and the supercapacitor is trickle charged actually from this battery. So we get the benefit of the high capacity by charging the supercapacitor, and we can draw burst loads for radio transmissions out of that, and we don't impact the battery life. In theory, we don't impact the battery life very much with this method. So the last part of this device is the sensing component, and because in our lab we are focusing on energy measurement and sort of smart grid type infrastructure, we chose to measure current. And the way we do this with this particular device is we measure magnetic fields emanating from current carrying wires, so things that go to lab equipment, heatings, televisions, lamps, things like that you might be interested in measuring. So in this case we use a giant magnetoresistive sensor to measure these fields, and the fields are proportional, the magnitude of the fields is proportional to the current in the wire. So if you measure the magnetic field, you can infer the current in the wire from that. There's a small problem with this sensor, that it draws a constant 2 milliamps when you power it, which you wouldn't think is a big problem, but if you think about the battery I just talked about, that is actually a big problem. So if we power this continuously, we would have next to no useful battery life. So the solution to that was to include a dedicated voltage regulator along with the preamplifier for this sensor that is turned on by the microcontroller just for the instant of sampling. So we do some processing, we sleep for a long time, we power this up just for a few milliseconds, take a sample and turn it back off. So that way we can get around this constant draw. So here's what the device actually looked like. This is a bit of an evolution of what we hoped it would look like and what it finally looked like. So on the left-hand side, you see a CAD model of what I hoped initially it would look like when I came up with this. You see on top, you see the microcontroller with its passive components and an antenna. You see a battery in the middle, and you see a sensor board on the bottom. So in the middle picture, we have the first physical build of this, which corresponds quite closely to the CAD model, but that was constructed before we started testing a few things, so some revisions were necessary for a working prototype, which you see over here. The size didn't change very much, but it did get a little bit more messy. So, the most notable things around here are that we have a large programming connector and a monopole antenna that takes the place of this chip antenna because we could not actually obtain the antenna that was spec'd. So this is from CAD model to a functional device. Well, how did we actually do when we tested this out? So we built several of these radios, and we were actually able to get a range of 200 meters transmission line of sight outdoors, which is a lot more than we expected because the use case for this device was sort of in a room maybe this size where you would install the device up by your lamp, up by your TV or something, and you would receive, hopefully in the vicinity, to gather data about the energy usage of your room, your lab, your industry. So Indoors, we were able to obtain penetration distance through several rooms in our building, and we were able to transmit all the way down the building in a corridor and outside the building. So this sort of exceeded our expectations. However, the runtime is still needs some work. Right now, we can get about 1 hour of runtime, sampling every 20 seconds and transmitting 42 packets, which corresponds to enough samples to reconstruct one cycle of a 60 Hertz current. So we can get an estimate of what the current is. What you see down here is the voltage on the supercapacitor as we go through a transmission cycle. Initially, the device is in sleep mode, so drawing almost no current. Then it comes out of sleep mode and turns on the sensor. So we have a few decoupling capacitors that get shorted up, so we draw a short burst current. Then we go into the regime of sampling 42 samples of the sensor and packaging it up for the network transmission, and then you see the actual network transmission, and then we go back to sleep. And the supercapacitor recovers from its use. So there's some work we can do in optimizing this period here, so we can make the entire transmission sampling period hopefully about half of that. We gathered some real data with this. We have a low current reading and high current reading. So the way these were taken is we installed the sensor at about 1 centimeter away from a current carrying conductor. It's isolated, so we don't have like a galvanic connection. That's the benefit, partially the benefit of this work, that you don't have to interrupt or even surround the conductor with some kind of pickup. So you can actually just paste it on to whatever conductor you have. And you see a few problems here. At low currents, low being 11 amps, because in this case we have a somewhat low gain that can be changed in the configuration of the hardware. You see that the reading is very nonlinear. So ideally you should have, this is an absolute value of a sinusoid, you should have peaks that go to the same height as all the others. But that's not the case. And this is a known behavior of the sensor, because at low fields, as per the specification of the sensor, it is supposed to exhibit nonlinearities. Unfortunately, they're not very well characterized. I wasn't able to find a good reference for the nonlinearities, so some work needs to be done on how to correct for that in post-processing. But at higher current levels, so we're talking about 70 amps in this case, we do get a very nice, pretty linear sinusoidal representation of the output. So from this, we can infer the current quite well. So what have we done? We have constructed a working wireless node that is very, very small using discrete components, and we have shown that it can actually be used to take real data, and it has applications that could be useful for laboratories, housing, factories, any place where you would be interested in doing energy monitoring and ambient condition monitoring. There are a few things that need to be done to make this really useful. One of them being we need to optimize the battery life. There are a few things we can do with that. One being that in this prototype, the battery is not exactly being trickle charged. It's directly connected to the capacitor. So every time you charge up the capacitor, you're drawing more current out of the battery than you need to be. So that's somewhat easy to fix, but we haven't had time to characterize that. And we can also add some energy scavenging. We can add small solar cells. We can add TEGs. We can add vibration and mount this in locations around the room, say on a hot pipe, hot steam pipe, on a vibrating machine, or on a lamp or anything like that, and thus increase the battery life and hopefully make it such that it doesn't need to be serviced. We can do some optimization of the software. I spoke a little bit earlier about shrinking the time that it takes to sample. We can also do other types of sensors besides magnets, and one of the things that I think is very important is that the chip supports wireless programming, so you can actually have many of these sensors in one room, and you don't have to go and plug into each one, reprogram them. You can actually address all of them at the same time, and it's reflash new firmware over the air. So if you need different sample rates, longer battery life, more samples, you can change all of these things on the fly. So we hope that this type of sensor is useful in aiding the transition from a standard grid to things like smart grid infrastructure and enabling the transition towards smart infrastructure and smart energy usage effectively. So with that, I would like to thank in particular our PI, Professor Wright, for supporting this work and funding the research. my supervisor, postdoc, now Professor Igor Paprotny, and graduate student Richard for helping out with testing the device. And with that, I would like to open for questions.
Thank you.